Okay, so good morning, everyone. We're going to continue with chapter 6, and we're going to discuss later on what will happen to the schedule that we have. So we started with chapter 6 last time, wherein we look at the concept of thermochemistry, the energy, potential and kinetic energy, the difference between heat and temperature. Okay. We also discussed some terms like endothermic, exothermic reaction, okay, the system and the surroundings, okay. And if I'm not mistaken, we end up with the concept of thermochemical equation. So when we're talking about thermochemical equation, so this is just an equation wherein we look at the energy that is involved in a given reaction. So we just write uh, usually a balanced chemical reaction, but you can change the equation that you have there to reflect on the energy that is associated with it. So for instance, the last slides that we have in our example, so we have here 2Na as 2 sodium metal reacting with 2 water liquid, producing 2 sodium hydroxide and hydrogen gas. So the enthalpy for that is negative 368.6 kilojoule. So what will happen? This is equivalent to the values of the number of moles here. So if you're going to adjust this one, you will also adjust the corresponding enthalpy, because as I told you, enthalpy is an extensive property. It depends on the amount. So if you're going to double this amount here, you're going to double the amount of the enthalpy. If you're going to half the amount of the enthalpy here, you're going to get also 1/2 of the enthalpy value here. Okay, so let's try to work on a particular problem. So you have here sulfur burns in air to produce sulfur dioxide. Now the reaction involves 9.31 kilojoules of heat per gram of sulfur at constant pressure. Write the thermochemical equation for this reaction. Okay, so if we're going to look at here, we are asked to write the thermochemical equation here of sulfur. So we just follow what we have here. So S8. So S8 would be what? A solid. And then when you burn, what material do you usually use?
CO2.
Okay. So anything that is combustible involves oxygen. And you know it's oxygen because the product that is produced is sulfur dioxide. So how are we going to simplify this one or write the balanced chemical equation? So you have 8 here, you have 1 here, so you add 8 there. So you 8 times 2 here, so this will become what? Also 8.
8.
And what else missing here? The delta H. So it says here, the reaction evolves 9.31 kilojoules of heat per gram. So what will be the delta H? Is a positive or a negative value?
Negative.
Okay, it's going to be a negative. But that's not the value, because that value corresponds to 1 gram of sulfur. So if you want to write the correct value here, you have to determine, okay, for every 1 mole of sulfur, how much is that? Because what you have here, this 9.39 is equivalent to 1 gram of sulfur. So if you want to get the delta H there, so you have here 9.31 kilojoules. Okay, so we can put a negative here because that's denote that it's released. So that is for 1 gram of sulfur. So what do we need to do? We need to convert the grams into what? Anyone? We need to denote the grams to moles. Okay, because we have one, we need to get the equivalent 1 mole there to determine the delta H. So we can put 1 mole here of S8. And what's the corresponding grams of S8 of 1 mole? All you need to do is multiply 8 to the atomic mass of sulfur. So you end up here with, what do you have here? 2.56.56, and you end up with this one.
Negative 2.39.
Okay, so negative 2.39 times 10 to the
Power of 3.
So that's the value that you're going to put here. So that is the thermochemical equation. Analyze. Analyze. Do you have a question? Question? Any question?
No.
Okay.
No.
So, have question?
Nope.
Okay. So let's try to see what this manipulation of thermochemical equation means, although I already discussed this to you last time. So when the equation is multiplied by a factor, the value of your delta H must also be multiplied by the same factor. And when the chemical equation is reversed, the sign delta H is also going to be reversed. Okay? So what does it mean? So we have the thermochemical equation of sulfur burning to produce sulfur dioxide. Now, what if the question is this one? Write the thermochemical equation for the dissociation of 1 mole of sulfur dioxide into its element. How are we going to do this? Anyone? How are we going to do this problem? So this is our starting point. And this is just the information that we need. Now you are asked now to get the thermochemical equation for the dissociation of 1 mole of sulfur dioxide into element. So what we're going to do with this reaction? Anyone?
Reverse it.
Okay, so we reverse it. Now, aside from reversing, what do we need to do also? Because remember, it says there, 1 mole of sulfur dioxide. So what does it mean? Aside from that, we're going to divide everything by
8.
8. So what we do here, the first thing we do is we reverse it, so we end up with this value. And what's the next thing that we're going to do? We divide that by 8. And we end up with a write-up like this. And the thermochemical equation would have what? A delta H equals to what? Anyone?
.99 times 10 to the second.
So I think that's what you have. So this is now the new thermochemical equation. So we reverse it. So this one becomes positive, and then we just need 1 mole. So we divide everything by 8 because we have an 8 sulfur dioxide here. So by doing it now, we get the correct answer. Question. Question?
No.
Everybody got that?
Yep.
Yes.
Okay. So what do we need to remember? So this stuff is not new to you. Okay. This is just the same as we do the stoichiometry before. But the way that you're going to do is you're going to apply the heat of the reaction. So you might have here a starting unit, and you're going to have a goal unit. So what's the starting unit? Maybe the grams of A. So like before, we have the grams of S8. And then what do? We convert that to the moles. And from that, we can get the corresponding heat of enthalpy that is resulting in the kilojoules of your heat. Okay, so remember what we have initially, we just have grams of S8 and the particular delta H for that. So what we're going to do is we convert that to mole S8, and we get there the corresponding value of the delta H. So that's the one that you need here. So let's try the same thing, but this time we change some of the value there. So you burn 15 grams of sulfur in air. How much heat is evolved from this amount of sulfur, given the thermochemical equation like this one? So what does this information tell us? Anyone? What does this tell us? So for every 1 mole of this, that's the energy that is released. Now the question that is being asked here, I have 15 grams of sulfur. How much heat will it release? So if you're going to go to the previous slide that we have, so we're given this one. And we're given the corresponding heat per mole, which is in your thermochemical equation. So the way that we're going to look at this is maybe to get the Q, which is the heat. We can get what? 15 grams of your S8. And then you convert that to moles. So you have 256.5. What did I have earlier? 256.56.
0.56.
Just want to make sure. Yeah, 256.56 gram S8. And then for every 1 mole of S8, there's a corresponding 2.39 times 10 to the 3 kilojoules. So if we're going to look at the units there, you cancel this out, you cancel this out. So you end up getting the corresponding heat at a given mass. Try to calculate what it is. So what do you get?
Negative 130 or negative 140.
Okay, so you get negative 140 kilojoules. So I'm going to leave this to you in one of these booster assignment that we have. So once you're done with, the deadline for the first 5 will be on Sunday, I think I put there to prepare you for the second and third exam. So this will be up soon. Okay. Now the next thing that we're going to do is how were they able to determine this heat of reaction? So the way that we're going to do is we're going to look first at the heat needed to raise the temperature of a substance, because this is the basis of our measurements of heat of reaction. Okay, so usually what they do for a corresponding value or amount of a substance, whether it is in grams or in moles, they measure, okay, the energy needed to raise at least, let's say, 1 temperature or 1 degree Celsius or 1 Kelvin unit. So there are terms that you need to know, and here are some of them. So we have the heat capacity, okay, and the specific heat capacity. So if you're going to look at them, they're almost the same in terms of the definition. So the quantity of heat needed to raise the temperature of the sample of substance by 1 degree Celsius. The only one that makes this difference, so if it's a molar heat capacity, that means for 1 mole. If it's a specific heat capacity, it is for 1 gram. Okay, so heat capacity, we could say, is a property that is constant for a given substance. Okay, so you don't expect one substance to have the same heat capacity as the other substance. So others would need what? Higher amount of energy to raise their temperature compared to the other substance that would need small amount of energy to raise their temperature. Okay, so that's what we call heat capacity. That's the amount of heat that you need to raise the temperature of the sample by 1 degree. So if you're looking at the value in terms of 1 mole, you call it molar heat capacity. If you're looking at it in terms of grams, that is specific heat capacity. And if you're going to look at the equation for that, okay, you can either have it like this or this one. So try to look at the difference that you have here. So here you have the C, which is your heat capacity. Here you have your S, which is your specific heat. Okay, so Later on, we're going to use this equation to solve some problem. Now, to give you a clear picture of on how you're doing this, I think some of you did this week, right? In their lab, because I was able to pass by the Wednesday morning and I see some coffee cup calorimeter there. Okay, so you have a device that is called the calorimeter. So this is used to measure the heat absorbed or evolved during a physical or a chemical change. So the one that you have is the one made up of styrofoam. Okay, so styrofoam is able to maintain the temperature that you have there. So the way that you call this is what? A coffee cup calorimeter. And this really is called a bomb calorimeter. So what happened is the reaction happened within them. And by measuring the changes in the temperature, you'll be able to get the energy needed, okay, to raise the temperature of a substance by 1 degree Celsius. So this is a classic, we could say, calorimetry problem. So how do they do that? What did you do in your coffee cup calorimeter? The first thing that you do is you calibrate your calorimeter. You use a hot water and a cold water. And whatever's the changes there of the temperature, you'll be able to determine the capacity, the heat capacity of your calorimeter. Okay, so the same thing here. If you have a bomb calorimeter, you put there some amount, and then you're going to determine what's the heat of reaction in that thing. So to give us some calculation problem, I have some example here. So you put here a sink weighing 35.8 grams, heated from 20 degrees Celsius to 28 degrees Celsius. Now you are asked how much heat was required. The specific heat of sink is 0.388 joules per gram degree Celsius. So what are we going to do here? Which one are we going to use among these two? The first one or the second one?
Second one.
Okay. So if you're going to look at the stuff that we have here, you have here a temperature from 20 to 28. And then you have there the specific heat, 0.388 joules grams per cubic centimeter. And then you have there the mass, which is 35.8 grams. So you have here Q, MS, delta T. So you're going to replace the one with the given one there, so 35.8 grams. And then you have 0.388 joules grams per degree Celsius. And then you have 28 minus 20. So if you're going to look at the unit, you cancel out, all that can be canceled out, giving you the unit of joules. And Q here is equals to what?
$111.
Okay. So that's 111. So what does the 111 represent? Anyone? What does the 111 represent? It doesn't represent, of course. So 111 joules That's the energy that you need to apply to change the temperature from 20 degrees Celsius to 28 degrees Celsius. That's what it means. That's the energy that you need to apply to raise the temperature that you have there. Analyze. Question. Question before we go on a challenging one. So this is the typical calorimetry problem that we have. So question. So the next one, okay. So this is, we could say, the use of calorimeter. So I think I need an extra thing here. So nitromethane, an organic solvent, burns in oxygen to the following reaction. So you have this nitromethane reacting with this one, producing carbon dioxide, water, and nitrogen. Now you have placed 1.724 grams of nitromethane in the calorimeter with oxygen and ignite it. Now the temperature of the calorimeter increases from 22.3 to 28.81 degrees Celsius. Now the heat capacity of the calorimeter was determined to be 3.044 kilojoules per Celsius. So write the thermochemical equation. So we could say we can use this equation that we have here. All we need to do is determine the corresponding delta H. Now, how are we going to solve this problem? So you have to take into consideration that you have a system here that is surrounded by a surrounding. What is the system that you have? What is the system that you have? Anyone? What is the system here in the given problem? Okay, so the system that we have here is the reaction. Now the surrounding is what? Your calorimeter. Okay, so the reaction released heat that was measured by your calorimeter. So the first thing that we can do is maybe get the heat of the reaction. But we're going to take this heat of the reaction from the perspective of your calorimeter. Okay, because what was given here is this one. So the way that we do this one, that is your C. That's your heat capacity times your delta T. So if we're going to look at that, so it's just 3.044 kilojoules per degree Celsius times the difference between 28.81 and 22.23 degrees Celsius. Oh gosh. Just try to make it clear here. So what does that correspond to?
Negative 20.03.
Okay. So you put a negative 20 there because that's the one that was released. Okay. Now you might ask, how do we know, Professor, that it was released? What is your guide?
It's negative.
You're the one who put the negative there. Okay. The thing is that you have here. So your guide is this. The temperature increases. Now, what does this tell us? Where does that 20.03 kilojoules came from? Because that was measured by the calorimeter. Now, the question is, where that it came from? Anyone? It came from this one. Make sense? The 20.03 kilojoules was released by 1.724 grams of nitromethane. Make sense?
Yes.
Try to understand it. I ask you, this 20.03, that was measured by the calorimeter. But the question now, who was responsible for that heat? So the one responsible for that is the nitromethane that you put there. So if we're going to continue on that, what does it mean? So for the 20.03 kilojoules, we put a negative there. That came from 1.724 grams of the nitromethane. And what we're going to do is we convert this to what? Moles. So what's the corresponding molar mass of your nitromethane? Because if you're going to look at this, we're just trying to get the delta H of this whole reaction. But we only have there the corresponding amount of heat for the amount or mass that was used. So what we need is to convert it to moles. It's just like making a ratio and proportion. So what's the molar mass of your nitromethane? It's around 61.04 grams. And from it itself, what can you say? Will the delta H per 1 mole higher or lower than 20.03? Is it higher or lower?
Lower.
Try to look at it. So that's 20.03 is 1.724 grams. So if you have 61.04 grams, so you expect the value to be higher. Okay. How much it is? Anyone? What's the number that you get? Negative?
709.
So if 1.724 grams release this one, 61.04, which is greater or bigger than 1.724, will release a much higher energy. So that's corresponds to this. So that's your delta H per 1 mole of that reaction. So if you're going to write the reaction, so you have CH3NO2, which is usually a liquid, and then 1/2 or what's that? 3/4 oxygen, and then you have CO2 gas plus 3 half H2O plus 1 half N2. And the delta H of that will be negative 709 kilojoules. Analyze. Analyze before we go with Hess law. Okay? So Hess law. So for a chemical equation that can be written as sum of two or more steps, the enthalpy change for the overall equation equals the sum of the enthalpy changes for the individual steps. That's Hess law. Okay? So Hess law, when reactants are converted to products, the change in the enthalpy is the same, whether the reaction takes place in one step or a series of steps. Okay? So you might have a reaction like this. Or you might have a reaction, let's say A, it becomes like that, and then, no, maybe that's not the way that we're going to do it. So let's say A producing D. But what really happened is A produced with B plus C, and then B plus C produce D. So if you're going to add everything, you cancel out the one on both sides. So you end up with A producing D. Okay. Now, why do they have to incorporate Hess law? What do we say about delta H earlier? Delta H is your, what? State function. So when you are a state function, it doesn't matter how you get there, only where you start and end. It's only the beginning and the end. The one in between, it doesn't care. Okay, so that's what we call your Hess law. Okay, now the main reason why you need to do this one is not all chemicals or substance or reagents can be measured their heat of reaction. Okay, so what you need to do is you have to rely on some known heat of the reaction, and when you combine them, it will give you the heat of the reaction that you're looking for. So for instance here, graphite producing CO. It's difficult to measure them directly. So what do? You find some known reactions that has the delta H. And if you combine, okay, the different reactions, most likely it will give you the reaction that you're looking for. So for instance here, you want to get the enthalpy when two carbon graphite reacting with oxygen produce CO, but it's different to do that directly. But what you know is you have this reaction. So two graphite plus oxygen producing CO2. Okay, and then two CO2 producing CO and O2. So what do? So you try to add them until such time you're going to get this overall equation. Okay, so if we're going to do that, what are we going to do here? So I have here 2, 2, right? So that means this should be by 2. So maybe I can put 2 here. I can put 2 here. I can put 2 here, and I multiply this by 2. Okay. Now here, we can also add here, multiply this by 2. So this will become now what? 4, 4, and this becomes 2. So that means you multiply this also by 2. Now what will you do? You cancel out the one that is common in the reactant side and the product side. So this one, 2 oxygen. What else? What else can you cancel? Can I cancel
That's
this? And when I cancel that, I only cancel 2 of the CO2 on this side. Is there anything I can cancel? Or maybe I made something, some mistakes here. I don't need to multiply this by 2, right? I'm just trying to make sure we got this right. So this is the original one. I don't think we need to multiply this by 2. Why? Because I'm just going to clean this up first. Okay, then I can go back. I can go back to that thing so it will be clean. Where's that? Oh, it's here. Try to make sure. Okay, so let's do it again. So this is what we have. So we say we multiply this by 2, right? So this now becomes, what do you have there? 2 times negative 787. And then, do we need to multiply this by 2? The second reaction, yes or no?
No.
no.
No. So all we need to do is we add them together. Before adding them, we can cancel out the one that we can find on both sides. So we can cancel this. We can cancel one of the oxygen here. So we end up with 2C graphite plus oxygen to produce 2CO, which is the one that we're looking for. And the delta H now is equals to, what do you get?
Negative 1353. Oh, is it? Okay.
Negative
1353.
1353.
2, 3. Yes.
Okay? So you don't need to measure them directly, but you're able to get the delta H. And this is through the concept of your Hess law. So another thing that we can look in this Hess law is the next one here. I think it's a concept check. So you're given the different reaction. More water, ice melting to water. The heat corresponds there is heat of fusion. And then water being evaporated to water vapor. The heat that you have there is heat vaporization. So you are asked there, how is the heat of sublimation enthalpy change for the reaction related to heat of fusion and heat of vaporization? So how are we going to do that? So we could just put it like this. And then this one. Right? So the one that being asked here is H2OS producing H2O gas. Because this one will just cancel out. And you have here the corresponding H fusion, H what we call vaporization. So the product there is H of sublimation. So if you're going to look at this, how are they related? Your H sublimation is just equals to the H fusion plus H vaporization. That's how you use Hess law in this problem. Okay? Question?
Nope.
So let's try to do this one. So we need a reaction like this. And what we have is these two reactions. So how are we going to rearrange this reaction here to get us the reaction that we need? Hmm? So what do we do? Okay, this one, H plus, where is H plus? None. OH minus, product side, right? H2O, reactant side. Calcium, product, reactant. So as you could see here, this one should be what? How do you call it during the election when the red becomes blue and the blue becomes red? There's a term that they use. You flip the reaction. And if you flip that, this one will become positive. Now, if you're going to flip that, what will happen? You're going to add it with the second reaction. And you want the second reaction, okay, when you add with the first reaction that was reversed or flipped to give you this equation. So what do we need to do with the first equation? After flipping it, we also multiply it by 2. Because if you multiply this by 2, what will happen? Okay, you multiply this by 2, I can remove the 2H plus here because they are on both sides. So leaving me with this and this as the product side, a reactant side, and this one, and the OH minus in the product side. Now, what will be my delta H? So the 111.8 is the one here. So you have to add this to this one. So what is the total delta H that you have? Anyone? So you have there negative 431. Is that what you get? For 31.2?
Yep.
Okay. So question so far. Because I'm trying to see if I can finish this today. We might not even need the fall. Something came to my mind. Okay. So I think I can finish this by today. So another thing that we do is the so-called standard enthalpy of formation. So how is this different from the previous one? This deals with the so-called standard states. And when you are in the standard states, that means the condition is 1 atmospheric pressure and 25 degrees Celsius. And the way that you put there is a delta H with a degree sign. So the way that you read this is delta H0. That's standard enthalpy of reaction. Okay, so what does it tell us? If you're going to look at the book, at the end of the book, there's the so-called delta H values of different reagents or chemicals. Now, usually, if you have these elements, they can exist in more than one physical state, and some elements exist in more than one distinct form. Just like your carbon, it can be a graphite or a diamond. The oxygen, it can exist as an oxygen gas or as an ozone. So these are what we call allotropes, the different form of elements in the same physical states. Okay. Now, usually the reference form is the most stable form of the element. So what does it mean? So usually the one that we call the delta H0, okay, that refers to the most stable form of the given element. So between oxygen and ozone, oxygen is the most stable form. So when you're doing this standard enthalpy of formation, this is just the enthalpy change for the formation of 1 mole of substance from its elements in the reference form and in the standard states. For an element, it is reference in the standard state usually 0. So what does this mean? So usually,
Professor,
yep.
we can't see the PowerPoint.
Oh. I think I didn't share it. So usually what we have here is whenever you have the elemental state, okay, the delta H of formation is equals to 0. If it's an element, but if it's other form, you can get its value based on the elements that it has. Okay. So the one that we have here, so for water, this is the standard enthalpy of formation. So we can also do it, let's say from this one, the standard enthalpy of formation to determine the delta H. But I would just prefer that we do it the one here. So how are we going to write the reaction here? The heat of vaporization of methanol. I'm going to go over the one that we're just going to focus on. So how are we going to go on the heat of vaporization here? So what form do we have? If I ask you to do it. So what's the states of this and what's the physical state of this one? Anyone?
Liquid to gas.
So you have a liquid to gas. And the way that we're going to look at the heat of the reaction here will be the summation of the delta H0 and just want to make sure. So this is the products minus the summation of N times the delta HF. This is your reactance. So what I'm going to do is I'm going to give you the delta HF of this one. So liquid methanol would have negative 238.7 kilojoules per mole. And then a gaseous methanol, you have negative 200.7 kilojoules per mole. So what will be the delta HF for the reaction? Anyone? How will I do this thing? So I have 1 times negative 200.7 minus 1 times negative 238.7. What is the delta H of reaction equals to?
$38.
Okay, so you have there 38. So what does this mean? How are we going to interpret this? For every 1 mole of methanol, you need 38 kilojoules to convert it from liquid to gas phase. Now, does this value make sense? You have a positive 38 here. Does that make sense? Does that make sense that you have an endothermic reaction? Anyone? Does that value make sense? Hello?
Yes.
Okay. So for you to vaporize your liquid to gas form, you need energy. That's why you need 38 kilojoules of energy to convert that from the liquid to gas. That's how you interpret this thing. And then I have another one here. Okay, so this is the one, the explanation that's given to you there. So methyl alcohol is toxic because liver enzymes oxidize it to formaldehyde, which can coagulate for the protein. So calculate the delta H for the following reaction. So I don't know, I mean, a year or 2 years ago, there are a lot of people that died because of poisoning after drinking alcohol in the Caribbean. Or my suspect there is the alcohol that they drink is not really ethanol. Okay, it's methyl alcohol, which is more toxic. So not alcohol are drinkable. Okay, so how are we going to solve this problem? So maybe we can assign the values that we have here. So you have here negative 245.9. Here, that's negative 150.2. And here, this is negative 285.8. What do you think the value here of the delta H for oxygen? Anyone? What did I say earlier? Usually the delta HF of an element is equals to 0. So what will be the delta H for this? How are we going to arrange that? So 2 times negative 150.2 plus 2 times negative 285.8 minus 2 times negative 245.9. So what do you get? Anyone? Anyone? What's the answer?
Is it negative 380.2? Or am I-
Very good. So how do we interpret this? What is the process? So if alcohol is burned, okay, it releases energy. Is that true? Maybe you cannot answer because you're not over 21 yet. Is it true that when you drink alcohol, you feel like, there's some heat in your chest?
Maybe.
Maybe. Okay, you're what we call, you can only drink when you're 21. My experience when I was 21, I already graduated from drinking. Okay, so the last two stuff that we have here, so the fuels that we need in our body. So usually we need them. They supply substances for the growth and repair of the tissue. They supply substances for the synthesis of the compounds used in the regulation processes. And then they supply energy. So whenever we eat food, what happens? The food that we eat reacts with the oxygen. So since it reacts with the oxygen, we have a combustion process. Okay. Now the question that I would like to ask, knowing this thing, glucose, which is a carbohydrate, will give you negative 28,100 kilojoules, while your fat would generate negative 27,820. So if you're going to look at the average value, the carbohydrate is what? 4.0 kilocalorie per grams, while the fats is generating 9.0 kilocalories per gram. So which is more efficient, the fat or the carbohydrates in terms of energy source? So this is a practical aspect question. Which of these is more efficient, a fat or a carbohydrate source? in terms of energy?
Fat.
The fat. But what's the problem with the fat? Anyone can explain? What's the problem with the fat? What's the problem with the fat? You can only utilize it when you don't have enough carbohydrate. Carbohydrate is the main source of energy. The fat will not be utilized unless there's no more carbohydrate. And what's the problem when you have excess carbohydrates? What happened to it? Anyone? What happens if you eat too much? Huh? This is just one of the practical applications of this chapter. So what happens if you eat too much?
Get tired.
You get tired? You have to explain it in that aspect that I showed you. I told you earlier, okay, the main source of energy is the carbohydrate. You can only utilize the fat when all carbohydrates are gone. Now the problem is what happens if you have too much of carbohydrate? When you have too much of carbohydrate, they become fat. Right? When do you gain weight? You gain weight by what? Eating too much. Okay? Because if you eat too much, you have too much carbohydrate, it will be converted to fat. But the thing is, you can only utilize the fat when there's no more carbohydrates in your body. So even though fat is an efficient source of fuel, that's not the number one source of your fuel. It is the carbohydrate. Okay? So, question before I turn off the recording, because I finished already the what we call the coverage for Gen Chem 1. So this is my farewell speech to you now. Because I'm going to go off the record to discuss to you what we're going to do for your final exam. Okay? So this is the